All right, heat affected zone. We have discussed so far the basics of carbon steels. We discussed some microstructures we would see in the welded metal. And now we want to discuss what microstructures we would see in the heat affected zone. And everybody talks about the heat affected zone. And I'm going to talk about the particular case of heat affected zone in carbon steels in traditional welding processes that are not so fast. Now, there are many other types of materials outside carbon steel, and there are many processes that are much more complex than the old traditional welding processes. But if we understand this particular and traditional case, we can make sense of pretty much everybody else. And later on in this class, we're going to have formulas to predict, for example, the thickness of the heat affected zone, whatever it is, which we're about to discuss. So it's good to have this very solid foundation on which we're going to be building so much. All right. So what is this heat affected zone I'm talking about, and you might have heard so many people talk about? Here we have a cross section of a weld, and when you etch it, you see something black there. Maybe that's a heat affected zone. Here's a crack, not pretty. And the crack is going through kind of a coarser grain there. So is that the coarse grain region you might have heard about? Is that the heat affected zone? Now it gets interesting. Typical steels end up being harder next to the weld. So is the hard part the heat affected zone? But in aluminum, it gets softer. So is the heat affected zone the hard part or the soft part? What the hell? Like in steels, X80, for example, that is thermomechanically processed, tends to soften in the heat affected zone. Old pipeline steels tend to harden in the heat affected zone. What the hell is going on? So I'm going to give you a really good definition because it cannot fail. And it's that the heat affected zone is anything that is affected by the heat of the weld. And what matters of this is that I'm not bound to say the heat affected zone is something I can see with my eyes in the microscope, like the black zone. And I'm not binding myself to say that the heat affected zone is what I can measure with a hardness tester, which would be the case of aluminum or X80 or traditional steels. And the reason is that sometimes the effects of heat are very subtle. And even if we preserve the hardness, or if we preserve the look of the microstructure at the magnification we're using, there might be changes in the material that might make, for example, really bad toughness, even if it looks like it should be fine, right? We can have problems of that type. So to be clear, when we discuss the heat affected zone, sometimes the problem can be easy, or sometimes it might require some very deep characterization. That said, in this disclaimer, we're going to be talking about the simplest case of heat affected zone in steels, in which things can be pretty well traced to things we have already discussed. But beware, sometimes the problems can be a lot deeper than they seem. But let's start with the easy first. So here on the left, we have a schematic of a cross-section of a weld, right? And this would be the weld metal, and all these weird looking grains, these are our heat affected zone, which we're gonna spend a good time discussing today. This curve here indicates what is the peak temperature this part of the material saw. For example, we know that if we are far, far into the plate, without doing any heat transfer calculation, we know that the heat of welding does not affect too far from the weld. We know this intuitively, and I will give you formulas to calculate it like right on. It's gonna be awesome. But we know that. We also know that right on the weld, we better melt something. The reason is because we're talking about fusion welding, right? And solid state welds also have a heat affected zone. But I don't want to discuss those type of processes now. I want to do the easy ones. So I know near the center line of my weld, inside the weld pool, I reach melting temperature. And in the center line, it's even higher than melting temperature. Some cases can approach boiling temperature. So right at the edge of the weld, in the fusion line, we would have melting temperature. And there's no such thing as real melting temperature. We have a solidus temperature and a liquidus temperature, right? That's why we have these two lines next to each other. To the left, thermodynamically, we would have only liquid. To the right of these two lines, we would have only solid. And in between, we have a mixture of solid and liquid. And as we go from melting to room temperature, we're covering all temperatures in between. Super interesting. Now, what we have here on the right is the iron-carbon phase diagram, which you studied in MatE 202 or whatever equivalent intro to materials course you have. We have been banging over this diagram for all of last week. And here it appears again. And what do we see? We see this. If we are at low temperatures, and this is to scale, the diagram and the schematic are together. So if we are at far from the weld, we would be at low temperatures. And at low temperatures, what we expect to see is this ferritic, pyrolytic microstructure far away from the weld, right? If the steel has this composition of this line, as it cools down from austenite, it would give us some ferrite and some perlite. We already discussed that. This is the type of things we would have done in Intro to Materials. If we move a little bit closer, now we would have that the maximum temperature that this piece of material sees kind of approaches the transformation temperature. So maybe I'm having some effects here. This effect would be tempering. If I approach the weld closer and closer, my peak temperature is higher and higher and higher. At this part of the weld, I'm in between the A1 temperature and the A3 temperature. I'm in the intercritical region where I have, and anybody cares to tell me where I have my red dot there? What phases exist there in equilibrium where the red dot is? Anybody cares to tell me what phases I have there? Or phase? Yes, thank you very much. This is ferrite and austenite. Thank you very much. So it gets interesting. And then in here, so the peak means we would have a mixture of ferrite and austenite. And here, if we get closer, we would have like all austenite. And depending on how close we're to the weld, we would have some austenite that reach low temperatures of austenite, or some austenite that reach high temperatures of austenite. We have already discussed many of these things, but we're putting them together. So let's look now at the thermal cycle of the weld. We're gonna spend 1 or 2 days talking about this in detail with formulas. But what do we see? You see this bunch of beautiful curves here that go from like narrow and tall to shallow and broad. This would be the temperature profile at a given time. So let's say at time 0, and at time 0 in this schematic is not too awesome, but we'll take it because it's what we have. At time 0, it says we would reach melting temperature And outside the melting temperature, everything is at room temperature. Okay, it's a little bit idealized, but I'll take it. And then after the weld passed at time, let's say time 2, now the temperature at the center of the weld starts going down, and then keeps going down, and keeps going down, and keeps going down. And what happened with all that heat? Well, as the maximum temperature goes down, that heat went out. And what we get to see is how the reach of the heat went from a narrow effect of heat to broader effect of heat to broader effect of heat. And it gets interesting because although the curve gets broader, it at some point, for a given temperature, it starts to become, this effect of heat starts to disappear because the temperature lowers and lowers and lowers. So whatever isotherm we have might be broader and broader, and then gets narrower and narrower again. This is if we see it as a cross-section of the weld. If we see it on the side, we would see that we could put thermocouples here. Thermocouple at point 1, point 2, point 3, point 4. And now we can see what the evolution of temperature would be at each position. And let's start with position, let's start with position 5. That is the farthest, well, 5 is far away. We see these heats a little bit, and then keeps going. As we get closer to the weld, 4, 3, 2, we see that the maximum temperature is higher. Of course, we had just discussed that. As we get closer and closer to the weld, the maximum temperature is higher, right? And so in 1, it says, well, the maximum temperature is such that it melted and then it cooled down. And if we are at position 2, that is right next to it, it goes close to melting and goes down, right? And what do we get to see here? Something very important. For the particular case of heat-affected zone in welding, definitely in the welding of steels, but this is pretty much every material, for the different points inside the heat-affected zone, that is a relatively narrow region outside the weld, they have essentially all the same cooling rate. They eventually merge and they all cool down. They go through a T85 all together. However, the peak at the heat-affected zone is different. So in the heat-affected zone, I'm gonna get into this in detail in a few slides, but I tell you now, in the heat-affected zone, we have many different microstructures, but we have the same cooling rate. So if we have very different microstructures, but we have the same material with the same cooling rate, what was different? Why do we have different microstructures if the material is the same and the cooling rate is the same? Why do I have different microstructures in the heat-affected zone? And I would like to hear a theory here in the chat. Different peak temperatures, exactly. So what matters in the heat-affected zone is the peak temperatures. So we tend to have like a knee-jerk reaction when we see different microstructures. We say, different cooling rates. And we have discussed so much about it. But in the heat-affected zone, the cooling rate still plays a role, but it plays a role for different types of welds. For a given weld, all the heat-affected zone is cooling down. We're going to assume in this course that it cools down all at the same cooling rate. Is it exact? No, it's not exact. Is it a good approximation? It's an awesomely good approximation. And but what matters is the peak temperatures. So let's look at this in these subzones which we had discussed, right? We have 5 subzones. 1, 2, 3, 4, 5. Yeah, 5 subzones, or let's say 6. One is nothing happened, unaffected base material. Then we have the tempered zone. That is something that did not transform, but got tempered because it got so hot. A partially transformed zone that corresponds to the intercritical region. And then we have two full austenization at low temperatures that people call crystallized or fine grain zone, and the austenization at high temperatures in which there is grain coarsening. And then the 6 would be the welded metal, which we discussed in the previous set of slides. Let's go through each of these in detail. Look, this awesome microstructure, Alejandro took it too. So you get a sense of what it looks like in the weld, in the microscope. So it's funny, as a mechanical engineer, when I was shown these photos, I was like, whatever, it looks like modern art, but they speak to me now. And what I hope to do in this class, that for those of you, whether you're mechanical engineers, materials engineers, or engineering physics, these images will start speaking to you. If they spoke to me, I think they speak to everybody by now. Look, here we have the weld metal. You don't see a clear line for the fusion zone. Actually, I'm collaborating with some friends in China who are welding titanium, and they cannot see the fusion line, right? It's very difficult, but you get to see a change in microstructure, right? In the weld metal, you get to see these lines. So we're gonna say the fusion line is here. This is not what I'm gonna be worrying about in this course for heat affected zone. But you see these big chunks here? This is the coarse grain heat affected zone. Check it out. These big prior austenite grain sizes. And then they get smaller, smaller and smaller. And look, here is quite small, quite small. What you see here, what you see here, it's quite similar. The difference is that here the austenite wasn't too hot and didn't coarsen. And here the austenite got to coarsen quite a bit. Let's talk about, this is the base metal, and we see the rolling marks, right? This is a rolled plate. You see, these are the marks of rolling. This is ferrite and perlite, I know. And then, look at this. We go from something that is clearly ferrite and perlite to something that is fine grain, right? A fine grain zone. But see how some of these darker, that small grain that is kind of gray, how it mixes it, how it blends with this other rolling structure in the base metal. This, where you see some of the fine grain and some of the previous ferrite grains of the base metal grains, this is in their critical zone. And then here, I'm going to show you a micrograph. This doesn't look all that different than this at this magnification. But when we get closer, you're gonna see that although this was below the transformation temperature, it still had the heat has had an effect and modified a little bit the look of the perlite. Super interesting. The thing speaks because we see these different morphologies. That means different peak temperatures. And we go from palm reading of these images, we're gonna go to heat transfer. And all is one and one is all. And the heat transfer from there, we're gonna go to the plasma physics that gives us the heat. And you don't get to choose, because if you weld something, doesn't matter if you like metallurgy or if you like plasmas, the moment you welded it, all of them were at the same time. And when you have a problem, you don't get to pick what problem you get. The problem might be that your arc was a problem. Your problem might be that your heat transfer was a problem. Or your problem might be your metallurgy was a problem. And because you took this class, you're conversant in all of those things. And you might be an expert at none, but you can talk to the expert in all. I think it's a good beginning. Base material. Here we go. Unaffected base material. All right. What is this white here? I would like somebody to tell me what these white chunks are here. Yes, yes, that's primary ferrite. What is this? What is the black that in this case looks quite like a giveaway? What do I have here? Perlite, really coarse perlite. You see, I have no doubt that this is perlite, but this one here that is black, if I didn't know the alloy, by the way, these are photos from our lab too. These are ours, so we know of welds done in our lab. This black could be many things, but for this alloy that we know, and we know that this is perlite. Okay, not big deal. I put that down here a few more like comments, but what I really want you to see is, yeah, primary ferrite and perlite. Look at this. This is the temperate zone. This is the primary ferrite you already told me. This is the perlite you already told me. Yet, we start to see how the perlite started to coarsen. If you look here, clear fingerprint, clear sharp edges in the unaffected base material. But if we get too close to the transformation temperature, we don't need to transform to start having like all these effects of diffusion in which we don't want to change phase, but we want to coarsen the phase we have. The reason is that interfaces take energy. So if I put enough energy in the material, the interfaces will try to go away. How do the interfaces go away? By coarsening. Okay, so now we see, same as before, ferrite, perlite, but the perlite is coarsened, right? And this is about, say, 75 degrees, between 75 degrees below A1, that is the first transformation temperature, right? Between 75 degrees below and A1. Okay. Partially transformed zone. These things start speaking. I hope they speak to you. Question, is this similar to reading a CCT in reverse? No, these things have many things in common with the CCT, in which I'm talking about primary ferrite, I'm talking about transformations. In that aspect is similar to a CCT. But what is different? In a CCT, we always start from full austenite. And then as we cool down from the CCT, we go from full austenite into whatever microstructure, and what changes is the cooling rate. Now, I never thought of this, but what we would like to do for the heat affected zone is like a CCT that has always the same cooling rate, but different starting temperatures, right? In the end, we don't do it in a dilatometer, we do it in a weld. So similar in many aspects to a CCT, but crucially different in that we start from all different temperatures, while in CCT, we always start from full austenite. Okay, this thing was talking to me. Primary ferrite, primary ferrite. I showed you this same image before when we were talking about the microstructures in the weld metal, right? Because here we have the intercritical region. Look what happens here. In this schematic, we have ferrite and we have perlite. This in image 1 is what corresponds to this, or to this, more or less the same. Ferrite and perlite. Now, if we heat it, say to 0.2, what happens? If we heat it to 0.2, Now, can I have perlite at temperature 2? Anybody wants to tell me if I can have perlite at temperature of 0.2? No, of course not. What I'm going to have is ferrite and austenite, because you already told me, right? And this is what we see, ferrite and austenite. And what transformed into austenite? What used to be perlite? If you do the cooling, you would realize that we have, just before crossing the line, have ferrite at this composition and austenite at this composition that transforms, this austenite transforms into perlite. When we heat it up, it transforms, the perlite transforms into austenite. And if I go a little bit higher, right, the austenite would grow a little bit, right? But look at this amazing, amazing thing. When I cool down ferrite, if I cool down ferrite, does the ferrite transform in anything? No. If I cool down to ferrite, the ferrite is ferrite. Ferritic steels, right? The steels that are always ferritic don't transform. Not so interesting. But how about the austenite? The perlite transform into austenite. And now I'm cooling down the austenite. The austenite does transform. The austenite transforms into what? Ferrite and perlite, right? And here we go. This is what we see here. These two images are so, this comes from a book, this comes from our lab. Look at this. You see this fine primary ferrite and the perlite. And here we have the original primary ferrite, then we have the primary ferrite from when we got into intercritical zone, and this is the perlite. This is quite amazing. Look at how much finer the ferrite is now. One way of refining the grain size in steels is by taking it to the intercritical zone and cooling down, because this way we what nucleates is this smaller ferrite, these ferrite grains. Okay, now we're into the grain refined zone, right? What happened here? Our peak temperature is into the full austenite, but barely above full austenite. So we barely had the energy to transform our ferrite into a full austenite and to dissolve the carbides. Because the temperature is not very high, whatever austenite that was nucleated, this austenite is not going to coarsen very much, and then it's going to cool down into what? It's going to cool down into ferrite and perlite, fine ferrite, right? And this is very similar to what we have been discussing all the time, right? This is what we saw in the intercritical region, except now there's no traces of the original primary ferrite. This is all small ferrite. Very interesting. So far, everything we have seen, and it makes sense. It's amazing. Now, poof, things became one big mess. What happened here? What type of transformation created this in a CCT diagram? What microstructure if I have a CCT diagram of this microstructure, what would it say it is? Yeah, a CCT diagram would say this is bainite. The CCT diagram would say it's bainite. A CCT diagram would say this is ferrite and perlite. Isn't that amazing? Same material, same cooling rate. Same material, same cooling rate. What is different between this and this? Look, same material, same cooling rate. Why is it so different, one from the other? What changed? peak temperature. And what was the effect of peak temperature? So peak temperature in itself doesn't have so much of a relevance as what did the peak temperature do? No, well, it's a different spot in the phase diagram, but what happens is when the austenite was so hot, let's go to the phase diagram here. Fine grain heat zone is around here. Coarse grain heat zone is here. Both are fully austenite, but now we have all these high temperatures that make diffusion very likely. We're not making a transformation by diffusing, but the grains are coarsening. Grains are high energy features. So if we give heat, it's going to accelerate at high temperatures, we accelerate the diffusion, and we have fewer grain boundaries. How do we have fewer grain boundaries? Bigger and bigger and bigger grains. All right. So what's a big deal? Why would a big grain give me this mess of a microstructure instead of a pretty ferrite and perlite? Why a big grain is giving me this big mess? So if you remember, something actually is for today's quiz, big austenite grains are very hardenable. Big austenite grains are the equivalent of having a very fast cooling rate. Or big austenite grains are the equivalent of having a high alloy content. The alloy is the same. The alloy is the same. It's just like the big austenite grain, and the cooling rate is the same. What changed here is a prior austenite grain size. And because now it became very hardenable at this, remember when we talked about CCTs, we said each CCT corresponds to one grain size. If we have different grain sizes, the CCT changes. What it does is as the grain size increases, the CCT moves to the right. And actually, one of the examples we discussed on Thursday had two CCTs, one in a dashed line, one in a full line, showing that how the one that corresponded to higher austenization temperatures had a bigger grain size and was more hardenable. So for the same alloy, with the same cooling rate, now we have something that is a bainitic structure. And we get to see here the FSA, we get to see the basket weave of acicular ferrite, right? We get to see this primary, in this case it's not so clear, but this primary ferrite here, marking an austenite grain boundary, right? We have everything here. All of these we can anticipate from like what we would see in a CCT diagram. Typically, the CCT diagrams that are made for welding are made with high austenization temperatures, so they would reproduce the coarse grain heat affected zone. So here we go. Why coarser austenite is more, okay, I have a very interesting question. We discussed this on Thursday, but I'll bring it up again. More hardenable means it takes longer to transform. Doesn't mean it's harder. It means it takes longer to transform, which often means that in similar conditions, more hardenable is harder. But the peak hardness of martensite is the same. And the soft hardness is more or less the same. Now, more hardenable means it takes longer to transform. And transformation happens by nucleation and growth. A big grain, and the nucleation tends to happen at grain boundaries because they're high energy plays. If I have a big grain of austenite, I have much more volume. My volume to surface area is much towards a volume and to transform that volume takes longer because we have fewer nucleation sites for the ferrite. Yeah, there you go. Thank you, Ale. All right, so look at this is kind of an ambivalent graph. It's kind of ambiguous graph. It shows something you do measure, hardness. Hardness is kind of some hardness in the base metal. And as you go through the coarse grain, the intercritical region, hardness increases, and you go through a fine grain heat affected zone, hardness increases, and by the time you get to the coarse grain heat affected zone, you have a very high hardness. Now, here you have grain size in the base metal. This is ferritic and pearlitic. What you have here in the intercritical region is ferritic and pearlitic too, right? We have two primary ferrites now in the intercritical region. In the fine grain region, we have ferritic and pearlitic too. And then it's funny, they talk about big grain size, right? And those of you who took an introductory course in materials, they would say, hey, isn't the story that like big grain size tends to be softer and small grains tend to be higher? And this graph is kind of ambiguous because they went from indicating the grain size of the ferrite. This is grain size of the ferrite getting smaller and smaller and smaller. And then all of a sudden they're indicating the grain size of the primary austenite grain, which is huge. The primary austenite grain is huge, right? But this is primary austenite grain in this part of the curve. And this is ferrite grain size in this other part of the curve. So what I hope is that the heat affected zone now starts talking to you because it says awesome things. I want to tell you something else about the heat affected zone. This process called tempered bead welding, in which you use the heat affected zone to your advantage. This is something that is used in some materials that are difficult to weld. And this is something I understand engineers prescribe easily. And if I get to hear from our real welders in the class, I understand the welders don't really love it because they constrain how much heat input you need to have, and they do it very tightly. So it's very difficult to weld because it makes you weld in a way that might not be what is natural to you. Big money salary, of course. Okay, so what's the story with the tempered bead welding? If you remember, and you are going to be doing this in the quiz, you can calculate the hardness of your heat affected zone. You might end up with something that is too hard, right? The NACE codes say have limits, ASME has limits at times. If it is too hard, what do you do, right? You can change the heat input and increase the heat input and would be somewhat softer, but there are physical limits to how much you can do. So what you can do is weld, get the wrong hardness, and then you heat treat. You can heat treat in an oven, but it's expensive and slow, and not all parts fit in an oven. Or if you can, for some alloys, in some conditions, you can try this trick. And if it works, you just save yourself a whole heat treatment. And it consists on this. This is the schematic of the heat affected zone. You see, this is a multi-pass weld. This works in multi-pass weld. And what it says is that the heat affected zone of a weld is going to be doing a heat treatment on the previous bead. But you have to do it just right. You don't want to overcook it. You don't want to overcook it. You don't want to undercook it. It's like a steak, right? You don't want it to be raw, or a pork chop, like let's say. Some people like their steak raw, but you should not eat pork chops raw, right? But it can be too tough if you overcook it. So this is just right. And so the weld that might be too hot with the heat of the bead on top of it, and we're going to be discussing in much detail all the thermal cycle of this. I have formulas for the hardness after one pass welding, and one of the projects I would like to assign for the grad students, if somebody would like to take it, is to find formulas for tempering, because that would be super interesting. We could design tempered bead processes from paper, and then we can test them, but knowing what we're doing. Look at this. Red is hard. Yellow and green is soft. And what we see here is a weld that if you do just one pass is very hard. How do I know? I know it because the last pass is all red. It's very hard. And you would grind it off, this part. You don't worry about this. But look at what is surrounding this weld. All this was built more or less on the same conditions. All this would have been all red. But as each bead goes over, it's tempering the previous bead, and we get to see this yellow here. We have a hardness mapper like this in the lab too. Those of you interested in welding, someday we're gonna reopen. You should see all the toys we have. It's amazing, right? This is temper bead, and we will have formulas to calculate the heat transfer. I hope to get the formulas to calculate the tempering, because then we'll be writing our ticket to riches. All right, I have time. I have 20 minutes, and I would like to discuss stainless steels. I'm gonna switch slides again. If you have any questions, you can fill them through the chat as I change set of slides.